This conference will now be recorded. This conference will now be recorded.
Very good evening, students. Today also we'll be discussing numerical problems from previous year's question paper, JEE Mains. And this paper I have taken up from 2020 5th September paper. Okay. So this question, let us read first and then try to understand it and solve it. A hollow spherical cell at outer radius R floats just submerged under the water surface. The inner radius of the cell is smaller if the specific gravity of the cell material is 27/8. With respect to the water, the value of R is. So basically, this problem is from Archimedes principle, as you know, floating law of floating. Okay, so from that part, and here there are two forces involved. One is buoyancy force, as you know. Sorry. So one is buoyancy force. So let me, before I tell you about the problem itself, let me pictorially represent the problem. So this is typical like representative figure. So this is the spherical cell, as you see, and it has outer radius capital R and inner radius small r, and you can see this cell is just submerged and floating. Okay, this is just submerged. So this is the top layer of the water. Just submerged means it is just under the top surface of the water. Okay, so this is the situation. So when this situation occur, when does this situation occur? In case of law of floating, you know that, isn't it? When the buoyancy force and the weight of the cell will be equal, exactly equal, then the cell will be floating, just submerged. Okay, just it will be just submerged or just below the top surface of the water. Here it is water. Okay, so this is the situation. So you know how to write the buoyancy force, right? Buoyancy force. So buoyancy force is given by the liquid. This is upward thrust, right? So this upward thrust is actually nothing but equal to the weight of the displaced liquid. Here it is water. So I have to find out the volume of the displaced water and density of the water. Let us take rho W. So this is spherical cell, right? I can write the volume. Now what is this R you should take? See, this liquid actually is displaced of this much volume. Okay, volume of capital R. Okay, so that's why I have to take R cube, capital R cube. Then rho W, this is the mass, and then G is weight. Okay, on the other side, see the whole cell has weight. What is the weight of the cell? Okay, weight of the cell is 4/3 pi. See, this is not solid one. Okay, so it doesn't contain mass inside. Okay, it contain mass only this portion. Okay, so that's why the weight will be less, isn't it? So it will be, see, so this is the volume of the mass content in this cell, and if I multiply with rho, the density of the cell, let us say rho s, then it is the mass of the cell, and this is the weight of the cell. So G we can strike out from both sides. 4 by 3 pi I can strike them out. Now what is given is this rho s by rho w. This is specific gravity of the material of the cell. If this is the case, see if this is if this is given as this is specific gravity. Specific gravity means the ratio of the density of the respective material with respect to the ratio, like to the density of the water. So it is the ratio of the density of the respective material to the density of the water. So this is given. This is very nice. Now we have to find out what is small r. Okay, that is the problem. So here I'll put rho s by. So I can just put here. See rho s by rho w into rq minus small rq is equal to capital R cube. Okay. So this factor I know is 27 by 8. So if I take it to this side, it will be 8 by, or I can write it here itself. So R cube is equal to R cube minus 27 by 8 27 by 8 R cube. Okay. So if this goes, that's a positive. This, okay, I'm sorry, this is actually R minus this. So it will be 27 by 8 minus 1. Okay, I have jumped one step here. So it will be actually 19 by 8 capital R cube, and this is small r cube. So we have to find out the value for small r. See, this we know, divided by this 8 we know, right? This will be 2, and this is 19 whole to the power 1/3, and this is r. See, 19 whole to the power 1/3, this has got a value nearly 2.67. Okay, this much. Okay, so what we got, 19 whole to the power 1/3 divided by 8 1/3. So this is actually 2.67, say, and this is 2. So if I divide this thing with 2, I'll get, then it will be 3.5 kind of that. Okay, 1.33 kind of that. And then we have to choose from the options where I get, see, this is nearly 1.6. Okay, oh sorry, this is 0.6. Okay, this is nearly 0.6. So this is not the answer. This is nearly 0.4, and this is actually nearly 0.3. This is 8 by 9. So it is actually, let me see once again, 2.6 means 1.6, nearly 1. Okay, so these are not nearly 1, but this, this will be 0.8, kind of that. I have taken this also approximate 1. So this is actually at least coming near to 1. Okay, I can see if I take best answer for, like, best matching answer, so I will answer this. Okay, so this will be the answer actually, 8/9. Okay, so this is made by 9. I don't know, somehow I am having doubt whether this is 9/8. Okay, I'll tell you this by cross checking whether it was 9/8 in the next class. Okay. Okay, so this question says three different processes that can occur in an ideal monoatomic gas. Ideal monoatomic gas. Okay, ideal gas. So we can understand it will monoatomic gas, PVRT. So it will follow ideal gas. Will follow this equation as shown in the figure. See, as shown in the P versus V diagram. So P versus V diagram, as you have seen, it will be kind of this. Okay, you look. So these are called isotherms. Okay, these are called isotherms. That means, okay, let me read the question itself first. So three different processes that can occur in an ideal monatomic gas are shown in P versus V diagram. The paths are labeled as A to B, A to C, see, A to B, A to C, and A to D. The change in the internal energy during the process are taken as EAB, EAC, EAD, and the work done as WAB, WAC, WAD. Now you have to find out the relations between the energies, okay, and the work done. Like, what will be the option given in the question? Okay, what will be the correct answer from this option? Okay, we have to find out that. See, first of all, let me explain this PV diagram. You can see this PV diagram. This is the carb one. Okay, so it has temperature T1. What does this mean? So this is actually an isotherm. Okay, an isotherm. Isotherm means if you take this point, this point, this point, or this point, or this point, everywhere temperature is T1. So similarly, the below isotherm, this also has temperature everywhere same, which is actually T2 throughout. Now let me tell you one thing. If the process is going from one point to another, okay, look, wherever it goes from A to B or A to C or A to D, the change in the temperature is actually, change in the temperature is T1 minus T2 or T2 minus T1, whatever it is, you take mod. Okay, so this is the change in the temperature. Okay, here T1 is greater, so T1 minus T2. So this is the change in the temperature wherever it goes. If it had gone from A to this place, or anywhere, so the change in the temperature is actually the same. Now, why I'm talking about this change in the temperature same? Because you know the internal energy is actually written as N. N is the number of moles, CV molar specific heat, and delta T. N CV delta T. This is the change in the internal energy. If the temperature changes, then this happens. Okay. But if temperature change, if the change in the temperature is same, then see this N number of moles, that is not going to change for the same gas, right? Okay, whatever process it may undergo, number of moles does not change. Okay, unless there is, okay, so that thing we have to take here, number of mole actually remain constant. Then cv is the molar specific heat. This is the specific what to say, characteristics of a particular gas. Okay, that cv does it has a fixed value always. Okay, this has fixed value. So once it has fixed value, then only thing which changes the internal energy, that is actually the change in the temperature. Since change in the temperature is same wherever it goes, whether it goes from A to B or A to C or A to D, the change in the internal energy is same. So that's why all three, C, E, A, B are equal to E, AC, AC or E equal to AD. These are all same. So we'll look where the internal energy change in the internal energy are same. So this first option likely to be the answer. Let me check with the other options. See, these are actually given different energies for different processes, which is not true. So first option likely to be the answer, but we have to check with the work done also. Now, when we talk about work done, we have to understand what are these processes. See, when the so look this AC process. Okay, AC is actually an isochoric process. Okay, an isochoric process. Okay, so in isochoric process, volume remains constant. So we know work done will be actually P into delta V. Okay, P dV. That means change in the volume and pressure. But here we look for the process AB, sorry, AC, the volume remains constant, so WAC will be actually 0. So work done, WAC is 0. Then we have to see where this option is actually, anyway, in the first option this is correct, right? So energies are in change in the internal is the same. So we can see WAC is 0, that is correct only. Now we look for the process A to B. Here delta V is positive, that means volume is increasing. Okay, so work done also will be positive, isn't it? So P delta V will be positive here. Okay, so AB is positive, this is correct. AC 0, that is also correct. What about AD? You look AD, this is corresponding to the volume, this one, and this corresponds to volume, this one. That means this is V2, this is V1. So here delta V is actually negative. Delta V is negative. So I should have got, because this is actually contraction. Okay, contraction, not expansion. This is actually volume contraction. So I should have obtained negative work done. So WAD should be like this, but in the answer you look in the option, this is the thing given which is wrong. But anyway, this for this typo you may get the number if you choose this option. Okay, see other options you don't have to see. When you see that the internal change in the internal energies for different processes are different, this is not true actually. Okay, all right. So the wise guess will be A, just by seeing the internal energies. Okay, all right. Let us go to the next problem. So this problem says number of molecules in a volume 4 centimeter cube of a perfect monoatomic gas at some temperature T at a pressure of 2 centimeter of Hg is close to. So here given mean kinetic energy of a molecule mean kinetic energy of a molecule is given by this in CGS unit, obviously. See, mean kinetic energy is given by 3 by 2 kBT. Okay, 3 by 2 kBT. And see, if I write ideal gas equation, PV is equal to N, this is the Avogadro number, kb into T. So here actually we have to find out at a particular pressure and volume, we have to find out this N actually. So let me write N is equal to PV is equal to PV by kBT. Now kBT, if we put the value from here, okay, so PV by kBT, in place of kBT I'll write 2 by 3 kinetic energy. Okay, so this K is actually kinetic energy. Now kinetic energy is given P and V. V is the volume given. P, how do you find out P? H, rho and G. See, G is given this one 980 centimeter per second square. H is given as 2 centimeter of mercury, 2 centimeter, and mercury has density 13.6 gram per centimeter cube. Okay, and G is 980. So if we put all these values, see P as 2 into 13.6 into 980, volume 4 centimeter cube, okay, divided by, see 3 I'll multiply in the numerator, 2 here, and kinetic energy is 4 into 10 to the power minus 14 ERG. Okay, so ultimately it will give you a number. Okay, so this number I have already calculated it. You can also try to calculate and see whether you get this number as 4.0 into 10 to the power 8. Okay, this is the number of molecules in a volume of 4 centimeter cube of a perfect monatomic gas, and with the given specifications or given informations like pressure is 2 centimeters of mercury. Okay, so this is how you have to solve this problem. So option 4 will be the correct here. Now let us go to the next problem. This problem says two capacitors of capacitance C and 2C are charged to a potential difference V and 2V. Okay, V and 2V respectively. These are then connected in a parallel such that in such a manner that the positive terminal of one is connected to the negative terminal of the other. The final energy of this configuration is, see in this case, see when I have two different capacitor charged, so I have total charge. So suppose for the C, it is actually charged up to V potential difference. Okay, so I have total charge here Q1 to be CV, and again another capacitor separately charged. So this has capacitance 2C and it is being charged up to 2V. So what is the charge here? That is 4CV. So there is the charge, right? Now how it is, how are they connected? Suppose this is plus, this is minus. For the other one, they are connected in parallel. So for the other one, it is plus, and this is minus. Okay. So this has 2C capacitance and voltage 2V to was having, okay, initially. Now say when they are connected, what will happen? What is the formula for the common? So common potential, let us say common potential is V. Suppose common potential after connection, common potential difference. What is the common potential difference? Let us say that is V. So that V, sorry, V prime, let us say V prime is given by C1 V1 plus, here I can write plus or minus C2 V2 divided by C1 plus C2. Okay, actually this is the formula. If this, see, if their terminals are connected in odd way, in the sense negative with positive and positive to negative, then we'll take minus here, okay, minus sign here. So in this case, what is the V prime? C1 V1 C V minus 2C and 2V, okay, 2V divided by C1 is how much? C, C2 is 2C, so I get 3C. So if I take the mod of that, you know, I have to take the mod of this, then I get 3CV, and in the denominator it is 3C. So what ultimately we get is V. So what is the common potential we have got? That is V. So what will be the final energy configuration? Final energy configuration will be, so equivalent charge is, since they are connected in parallel, so equivalent charge will be 3C, that is for sure. This is equivalent charge since they have been connected in parallel. So final energy of this configuration is, you say, that is half CV square, right? Half CV square. C is 3C and V square is V, half 3C. Okay, so then we can see this is actually 3 by 2 C V square. I think this is the answer. One answer is there. Okay, I see this V squares are not written here. There are typos anyway. So this is, these are the options. So 3 by 2 V square is the correct answer for this question. Okay, so final energy configuration is 3 by 2 CV square. Okay, 3 by 2 CV square. C will also be there. Yeah. All right, so this is the answer for the given question here. So here the turning point is that we should not get confused that whether the net charge will be C for both of them. Okay, no, it is actually 2, because charge will not be getting destroyed, isn't it? So see, this has got C1 charge, this has got C2 charge. Okay, some sorry, here it is 4CV and here it is CV, so they will get actually added, okay, when we use this two separate capacitors in combination, in parallel combination, basically the charge will be actually added up. Okay, 3C, sorry, capacitance, they are parallel, so capacitance will be 3C. And also we have seen that the sign over here, the sign in this case, since they are connected positive to negative, negative to positive, like that, so that's why the this sign will be minus here. C1 V1 plus C2 V2 divided by C1 plus C2. Instead of plus, we'll write here minus. So that this is where the turning point lie. Okay. So what to take the charge and what to take the formula for the common potential. Okay. Now here is another question. An electrical power line. An electrical power line having total resistance 2 ohm delivers 1 kilowatt at 220 volt. Okay, the efficiency of the transmission line is approximately. So you know what is efficiency is? Efficiency eta is actually power output by power input. Power out by power input. Okay, power output by power input. So this is actually the efficiency, and with multiplication of 100 we'll get in percentage. So this is the thing. Now here see, the line has total resistance. It has certain resistance as well. That means there will be some power loss, isn't it? So what is the power loss here? How to find out? I need to know the, say, resistive loss will be I square R only, right? I square R. I have to know the current in the line, and I know R is, capital R is here 2 ohm. So then I can get actually the lost power. And if I have to get 1 kilowatt input, then I have to give surplus of this much lost power, okay, in the input. If I have to get in the output 1 kilowatt, since this line has 2 ohm resistance already, there will be some resistive loss. So I have to give this input to be, so power input will be this 1000 watt plus loss. So this total will be the power input to get this 1 kilowatt. Okay. So for that, see, if we want to find out what is power loss due to this resistive loss or resistive heating, I have to find out what is the current in the circuit. So how to get the current in the circuit? We know P is equal to VI. V is given 220. So I will be P by V. Now what is the power loss? Power loss will be I square R. Okay, I square is P square by V square into R. Okay, P square by V square into R. R is 2. So I'll write directly 2. 2 P square by V square into this. So what is P is 1 kilowatt, isn't it? So let me first find out what is the lost power. Lost power. P square by V square. Okay, that means this P by, okay, 2 into P square by V square. V is 220. Okay, this is what we have to, we have got this. With this we have to add the 1000 watt, as so we will get, you know what we will get. So output, power output is 1000 watt. That is what given in the question, but power input we did not know, so that will be at least this. Loss of power, power loss due to resistive heating into 100. Okay, so this part, if you check, it will be nearly 41. Okay, nearly 41. All right, now if I write P loss to be 41 here nearly, then I will get here 1041 into 100 here. So this, if you try to see, if I go for this 1041, let me just take this to be 40 itself, okay, for the sake of calculation. So this is greater, so I have to take point, this will come here. So you look, if I multiply 9, so this is 0, 9. Okay, now this will be 4. Okay, so this is actually the 1. Okay, so now if we multiply, okay, so one more I can get from here. Okay, so I think I'll just multiply this. Okay, so it will come around 5 here. So nearly, actually you will get nearly 96%. Okay, so this is the answer here. You look, this is the answer. So you have to do it with a very quick calculation, but it was, see, I'll tell you the turning point here for this problem. See, each problem there is a turning point where you might be lost. Okay, so while solving, you need to see that this line has got this much resistance, so there will be power loss obviously. So here only input is given this. Okay, so sorry, output is given, delivers 1 kilowatt, output is given, input is not given. So how do you get input? If you give input 1 kilowatt, do you think you will get 100% efficiency? Actually there is nothing which gives 100% efficiency. Okay, so it is not possible. Just by giving 1 kilowatt to the line, you get 1 kilowatt itself. Okay, so what extra or surplus input you have to give? You have to actually compensate this loss due to this resistance. Okay, that is this I square R loss. Then if you give this surplus input and an input, then you might be expecting to get 1 kilowatt output. Okay, so this was the turning point here. Okay, you have to find out the loss and you have to add with this 1 kilowatt to get the input. Okay, that was the important point, and rest of the things are calculation, you can do it. Now there is another good question. So this is actually from galvanometer, moving coil galvanometer. A galvanometer of resistance G is converted into a voltmeter of range 0.1 volt. That means, you know, when okay, by connecting a resistance R1 in series with it, so it is given. So suppose there is galvanometer, okay, galvanometer coil. Okay, so this has resistance G, it is given actually. Now it is converted into a voltmeter just by connecting a resistance, that is R1 here. So when it is connected in series, this R1 resistance is connected in series with G, then it becomes a voltmeter of range. See, the range is actually 0 to 1 volt. That means I can take this, that the voltage across this now will be voltage across this, or this can show the maximum voltage to be 1 volt. Okay, 1 volt. That means what? If, see, but here one thing is clear, that here IG I don't know. So how to write here? See how to like this situation, how to write here, IG whole into G plus R1. This actually will give you the 1 volt. Okay, this will give you 1 volt. This is the range meaning. Okay, this is the meaning of the range of the voltmeter, 0 to 1. Meaning, if I would have written 0 to 5, then I would have written here 5. Okay, so this, the upper limit we have to take always. So Ig into R plus G, sorry, R1 plus G, which gives you the range. Okay, range of the voltage. Now look the question. The additional resistance that should be connected in series with R1 to increase the range of the voltmeter from 0 to 2V. It is now easy, right? So from here, let me do one thing. Let me get Ig. So Ig means current through the galvanometer. So which will be able to provide full scale deflection. Okay, this is actually the current in the galvanometer. So in the question it is said, if you add, so what much, like how much resistance you should add so that you get the range to be 2V. So let us say some R2 is added with this. So how do I write that? I have now circuit G, I have R1, and then I am connecting additional R2 resistance so that I get the range 2 volt. That means what? I can write Ig into R1 plus R2 plus G, which is equal to 2 volt. Okay, now I did not know what is Ig. I can find out from here. Ig is equal to V by G plus R1. So from here I can write. So Ig is actually, okay, let me write it here, 2 volt. So R1 plus G plus R2, which is 2 by Ig. What is Ig? Ig is actually V by G plus R. V by G plus R1. So this is actually thing Ig. Now what is this R2 then? R2, we get here it was 2 volt. So 1 volt, 2 volt, that will be cancelled. So 1V and 2V. All right. So V volt and 2V volt. So VV got cancelled. So I get here 2 of G plus 2 of R1 minus G minus of R1. So I get G plus R1. That's R2. So I have to actually add additional resistance, that is G plus R1, to get the range double. Okay, 2 volt. 0 to 1 volt it was earlier. Now to make it double, you have to additionally add another resistance, that is R1 plus G, in series with the galvanometer to get 0 to 2 volt range. Okay, in this converted galvanometer. All right. So here also turning point is that you have to somehow find out Ig, and also you need to know what are the formula, like how the range, like how do you actually understand the range. Range is nothing but the drop of voltage, drop in voltage. Okay, the voltage drop across the G plus the voltage drop across the resistance connected in the series. Okay, all right. So this was D, option D. Now we'll try to solve another problem here. It is given a square loop of side 2A is carrying current I is kept in the XZ plane. Let me show you what is XZ plane. See, suppose this is your Z. I'm sorry, this is X, this is X, and this is Z. So this is the horizontal plane. Okay, you can see that. So this is XZ plane. So a square loop of side 2A carrying current I, you can see that this is kept in current I is kept in XZ plane with its center at the origin, the axis system, Cartesian coordinate system. A long wire carrying current, same current I, is placed parallel to the Z axis and passing through 0, B, 0, where B is much greater than A. So what does that mean? It is meaning that there is an axis which is passing through the y-axis. So there is a current carrying wire which is passing through the y-axis at a distance B from the origin and which is parallel to the z-axis. These are actually the meaning over here in this problem. Now rest of the things will be clear to you. Now see, I have got, okay, the question is here, the magnitude of the torque on the loop about z-axis. You have to find out the magnitude of the torque. You know what is torque? Torque is given by, in a loop, torque is given by M cross B, right? M cross B. Okay, that means MB sine theta. If theta is 90 degrees, then the torque will be maximum. But what is this M? M is actually magnetic moment. Magnetic moment is given by the current in the loop and A, that is the area vector. This is a vector quantity. This is the area vector of the loop itself. Direction of the area vector of the loop itself. So the direction of the area of this loop, like okay, outer normal. So this will be either positive y-axis or negative y-axis. Okay, but you know how to take that. Suppose this is a loop, circular loop in the horizontal plane, and if the current is flowing like this, then you know magnetic moment, you can just use the thumb rule to find out that it will be in this direction. Okay, this will be magnetic moment, which is written even in terms of mu also, magnetic moment. Okay, the direction of magnetic moment we can actually, so here the direction of magnetic moment will be along the y direction. Okay, y axis, that is for sure, you know that. Okay, why it is here? So it is actually, say if you just use the right hand thumb rule, then like in grip rule actually for the loop. So the current is fine. So A is actually, A is along y direction. Okay, this is very clear. Okay, along y direction. Now what is B? What is B here? B is the magnetic field created by, so magnetic field created by this long wire which is also carrying current I and which is at B height. Okay, B is the height, suppose. Okay, B is the height from the origin. Then it will actually produce magnetic field since it is carrying current, right? It will produce magnetic field around it. Okay, so what is the magnetic field here which is actually passing through, see, or linked through this, or providing force to this loop. So that is the magnetic force, sorry, that is the magnetic field B I have to find out. So for a long straight wire, you know, if you are, if the current I is passing through the current and you are calculating the magnetic field at some point like this, okay, at this point P, it is R. So I have to actually write the use the Ampere circuital law to find out the magnetic field at this point. Okay, so this will be mu 0 I this side, and left hand side there will be b dot dl, b dot dl, that means 2 pi b. Okay, 2 pi b, okay, b dot dl into b. So this is actually mu 0 I. So that means what? B magnetic field will be mu 0 I divided by 2 pi b. Okay, this is actually the magnetic mu 0 I by 2 pi b. This is the magnetic field which is actually providing the force to this loop. Okay, now we can find out the torque. So m is actually I into a, I is I into a is 4a square, I a, b we have got mu 0 I, mu 0 I by 2 pi b. And what about the angle? See, magnetic field in this place will be actually will be the down. Okay, so ideal cross b is anyway in the z direction, or here in this case m and b, m is along y direction, so that we have seen, and b is the magnetic field direction. It will be actually, so if I look here, it will be just low radial direction. Okay, radial direction like this. Okay, so okay, so this tau will be actually, okay, we have to, I think we have to get the magnitude. Okay, no need to go for the direction. The magnitude of the torque in the open loop. Okay, so on the loop about z axis, oh I'm sorry, so about z axis, so this is actually about, so about z axis you have to find out. Okay, torque, that means the perpendicular distance mb. Okay, so anyway, so the torque is actually, the magnitude of the torque will be mb. Okay, so here m is along the this direction, and b will be such. Okay, so at this particular, so it is down row, right? So this will be, magnetic field will be actually in this direction. Okay, magnetic field will be in the x direction. So these are actually 90 degree. Okay, this is z, right? this is Z, this is X. So at this particular position, the magnetic field will be curling around, right? So the magnetic field will be down, right? This is just like this is Z axis, and this is Z axis, and this is the current. So this is the above the Z axis. So here current will be, this direction, the magnetic field direction will be. So this is perpendicular to again y direction, okay, perpendicular to y direction. So that's why it is MB sine 90 degree. So it is MB sine 90 degree. All right, so B will be along X direction, okay, according to the given configuration here. M will be along Y direction. So M is, I know, I into A square, 4A square. B is mu 0 I by 2 pi B. So this is the one. So I get 2A square I square, and obviously mu 0 will be there. Mu 0 into 2 I square A square divided by pi B. Okay, pi B. I don't know what are the options. Yeah, so this is the actually option here. 2 mu 0 I square A square divided by pi B. Okay, so 2 mu 0 A square into I square divided by pi into B. So this is actually the torque. Okay, magnitude of the torque on this loop about Z axis. So now there is another question. I hope you are able to read this properly. An electron is constrained. That means it is actually bound to, okay, it is constrained. Constraint means it is made to move by some external agency. It is actually compelled to move. An electron is constrained to move along y axis with speed. So let me draw this Cartesian coordinate system. If I, this is y, this is z. So an electron is actually confined or constrained to move in the y direction with velocity 0.1 c. This is the velocity. Now it is c is the speed of light, as you know. In the presence of electromagnetic wave, whose electric field of the electromagnetic wave is given here is equal to 30 j cap sine 1.5 into 10 to the power 7 t minus, that means omega t minus kx. Okay, this is k volt per meter. The maximum magnetic force experienced by the electron will be, so force, force is v, v q v, that means q into v cross b actually. So this is q into v cross b. If you write in terms of vector, q into v cross b, this is the magnetic force on a charged particle. Okay, so how to find out v? So v is actually, sorry, v is given already. V is along the direction of y. And what is this b? See, here the electromagnetic wave is propagating along positive x direction. Okay, positive x direction, because it is minus kx, so it is propagating along positive x direction. So I have to get the, see, if I say I j k, the propagation direction k will be got from E cross B or H, E cross H. Okay, so E cross H, so E is Y here, cross H will be such that K is I. So E cross H means this. So So H must be along the z direction, so B must be along the z direction. That is fine. Okay, that is fine. So E cross B or H, that is along the z direction. I have to find out what is the maximum magnetic force, that means magnitude of the magnetic force. So how to find out magnitude of the magnetic force? This is B, Q to V cross B. Q is given as 1.6 into 10 minus 19. So, and we have found out the direction of the V is along the direction of Y, and B is direct in the direction of Z. So this will be QVB sine 90 degree. Okay. So QVB is known. V is given as 0.1 C. So B is done. What is B? B, actually here I have to find out the amplitude of the B here. See, we know there is a relationship E0 by B0 is equal to C, right? Then B0 will be E0 by C. All right, E0 by C. So E0 by C means how much? So what is B0 then? B0, the magnitude of the magnetic field. So 30 by 3 into 10 to the power 8 meter per second. So this will be actually 10. So this is actually 10 to the power minus 7. This is actually 10 to the power minus 7. Okay, Tesla in SI unit. So we have got B also 10 to the minus 7. Let me just put these values. Look this magnetic force. Q is 1.6 meters minus 19 coulomb. V is 0.1 into 3 into 10 to the power 8 meter per second. Okay. QV B is 10 to the power minus 7. Okay, like that we have got. So if you do the calculation, let us see how it goes. So 16, 3, I'll keep this, and this 0.1. So 10 to the minus 2 will be added to it. So this is 10 to the minus 21. Okay, and from here it is 1 is cancelled, 1 will be there, so 10 to the minus 2. And now look, this is actually around 48. Okay, so 48 into 10 to the power minus 20, this is actually the Newton. So if I want to write point 1 C, okay, let me check if I have written something wrong. 1.6 minus 19. Okay, B I have to calculate. This is volt per meter. C minus 8, 10. Okay, so minus 7 only, fine. Okay, so if I want to write in terms of 10 to the minus 19, I have to divide with 110. Okay, that is what is given in terms of this. This is the answer. Okay, 4.8 into the minus 19. Okay, this was very simple problem, unless you understand this, that you have to find out the magnetic field from this. This is a question combined with the concept of moving charges in the magnetic field, and also the electromagnetic theory. Okay, electromagnetic theory, simply like the direction here at least not mentioned, the magnitude of the magnetic field, how to find out the magnitude of the magnetic field. So that is was the turning point here. Okay, that was the turning point here. Okay, since mass is not involved here, Okay, so mass is not involved here, so otherwise would have go for the would have been gone to the relativistic regime to find out the mass. Okay, this is actually relativistic speed. So at this speed, time actually mass will be uh, more actually. Okay, m0 by rest mass energy, rest mass is m0, so m0 by square root of 1 minus b square by c square. Okay, anyway, those things are not here, at least in this problem, since we have bqv. Now I think this is the last question for today's session. The question says, with increasing biasing voltage, a photodiode voltage of a photodiode, the photocurrent magnitude, okay, photocurrent magnitude increases initially, after attaining certain value it decreases. Okay, it increases linearly, it increases initially, it saturates finally, and it remains constant. Let me show you the figure how it goes. Okay, see, this is the curve IV characteristics for a photodiode. If you increase the voltage, first current will be increasing linearly, okay, and then it will saturate to a particular value. After that, the voltage does not, sorry, current does not change. Photocurrent does not change with voltage even if you increase. Okay, so option third will be the correct answer. So this curve, better to remember this curve, or just keep a view in your brain. Okay, this is the photodiode. Okay, photodiode diode current. Okay, and obviously this is another point to learn here, the current versus voltage. See, uh, in this, when you increase the biasing voltage, see, biasing voltage and current both are positive, but the current is negative. Okay, this is in the third quadrant. All right, so this is all for today. Thank you for your patience. We'll take up the remaining questions tomorrow, and also I think we have to go for day after tomorrow also. So bye for today. Thank you for your patience.